All right, so we're in the middle of talking about trees. We're gonna start getting to the bulk of it today. Some of the really good stuff. Assignment was due last night. I am very close to releasing the next one. It's almost all put together. I just have to put the finishing touches on it, figure out how I'm grading it, and then upload it. So that should be up for you today. I anticipate you'll have about a week to work on it. There are two parts to it. There is an on paper hash version or hash section that has you using some hash functions and playing with some different collision types to see how to fill a hash table with a very obscure hashing function. Then there is implementing quicksort and merge sort on your singly linked list class, right? Since the hash part is a little bit longer, I cut doing it to your list and insert it with a linked list just so they don't do a ton of extra value in doing it for the extra. Questions before we dive into trees?
So that when we do next Thursday.
Something like a week from now. All right. So last time we were talking about what goes inside of a tree node and what goes inside of a tree. Barely visible. So we talked about how we have some data for a tree node. We need to store the children. If this is a binary tree, they have separate things for the left child and the right child. So they'd be tree node of T left child and tree node of T right child. But since this is just, we're still talking about trees in general, you would store the children in an array. If we know exactly how many children there are, and that's consistent across all nodes in the tree, then you would want to store them as separate objects and not as an array. So this does not hold true for a binary tree. The tree object itself is made up of tree node objects. So we only really need to store the root for the tree object. Everything else is some kind of algorithmic process from starting at the root and doing something there to explore the rest of the tree. The method we care about, we want to have, we take a node and element returns the data of that node. Get root returns the root of the node. Parent also takes a node and returns the parent, not the parent, the parent of that node. Wherever there's a V there, that stands for vertex, which for our intents and purposes is a node. But as we start getting into graph terminology, nodes are called vertices. So if you see anything like that with a V in it, it stands for vertex, which means node. Children of V returns some kind of iterable container. This could be an array list, it could be a linked list, something that has an iterator that you can get an iterator for that holds the children of that node. And again, if this is a binary tree, we don't necessarily need that. You would have something like for each node, you'd already have to get left child and get right child of a particular node. Then we have some booleans, is eternal, true if the query node is internal, false if it is not. Is external, true if it's external and false if it's not. Remember that internal just means not the root and external just means the root. So is external could be implemented as basically is root. Look, is root. Size tells you the number of nodes in the tree. Is empty just tells you whether the size is 0. And then positions is another iterable container for all of the nodes in the tree. So you need some way of accessing every single node in the tree structure. And then elements is an iterable container. So yeah, all nodes. The content of all nodes. So an iterable container of all of the data versus an iterable container of all of the nodes. Question?
What is the difference between is external, is root, or are those the exact same?
They're basically the same thing. So you can just implement them as the same thing. It's. There's also a replace that allows you to pass in a node and some kind of data, basically replacing the contents of that particular node with the new value E, and then it returns the old contents of that node too. So it's kind of like an update in a list. So there are also some things that we can do for something like each node in a tree, like figuring out how deep that node is. How would we implement that? We have a tree object. We have a node in that tree. How could we figure out how deep it is? Let's first assume that it has a parent reference. If it does, this process is a bit easier. Yeah,
You just check to see if it has a parent until the parent's like null.
until the parent either is null or is the root, yeah. So you're just gonna go parent, 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 incrementing a counter each time. And then once you hit the root, you know that you're done and you can return the value of that counter. What if you don't have a parent pointer or parent reference?
Same, let's start out.
Yeah, we talked about that, the fact that each node having a parent reference was optional in the tree node. So if each of these nodes don't have a parent reference,
You don't have to start with root, just do like.
yeah, we need to have some kind of search from the root to try to. We need some way of going through all of the nodes in the tree and saying, are you this node? Are you this node? Are you this node? Are you this node? Until we find it, and we keep track of the current depth that we're at as we do that. Does anyone have an idea of how you might do that? How could we search the entire tree? There are two ways that are done in practice. Oh, what, sorry? Recursively, we definitely could. How would we do it recursively? What would that look like? We keep track of the current depth and we say, is the current node the query, the node that we're looking for? If it's not, then recursively look at the left child and the right child, or every child that's in the tree, where I'm assuming it's a binary tree. So you look at its two children, but if it has more children than that, you just add them all. You have a list of for each child. Use a for each loop, then repeat this logic on that child. You could do that. Is there another way?
You just start at the top and just go down one individual branch each time and find somebody that accompany them, just start with the here.
Kind of. So rather than recursively, we're actually going to add each child to a queue. So if we instantiate a queue object and say, all right, here's a to-do list, basically. And starting at the root, we're going to add all of the root's children to this to-do list. And then for the left child, all of its children, we're going to add those to the to-do list. Then we dequeue the next node and say, are you in? For all of your children, add them to the to-do list. What's the difference between those ideas? So if you have a recursive solution versus a queue solution, what's the difference? It'll still search the whole tree, but the recursive version will kind of look like, let's see if I can do this justice. Not really. It does it explores down here, it kind of does this process. if I give you an actual tree, it probably makes more sense. It's back here. I don't know what that is. Second grade art. So we have an actual tree structure. I'll use the typical depth. Talk about it. So we're gonna ask, is this the query? Is this what we want? No, we're going to recursively explore the left subtree, and when we return from that, we'll explore the right subtree. So we're gonna ask about this. And then we're gonna ask about this, and then this, and then this, and then this, and then this. So we get this type of structure. So we kind of iterate it in that way. If we use the queue structure, we're doing it in what we call level order, where we kind of just do this. Because here we're gonna add both of these to a queue, which means the next two things we're gonna do, explore, are those nodes. When we explore this node, we add these to the queue. When we explore this node, we add these to the queue, and then we go through those in that order. So it's a little bit different, but it explores the entire tree structure. We'll talk about what these are called, we'll talk about how we can implement these momentarily, but I just wanted to talk about it. We wanted to figure out the depth of a particular query node, and we don't have access to the parent. We can do this either way. Whenever we make this recursive call, we increase the depth. Whenever we come back to it, it's decreased for us. All right. How do we determine its height? We have a tree structure, we need some way of determining how high it is.
The branches have different heights themselves.
Yeah.
Oh, they did.
If it's balanced, then they have to be plus or minus one from each other. Or plus or minus, I guess, double or half if it's a red black tree. Yeah, it's very similar. We have to search for the deepest node and keep track of the deepest node that we've seen so far. So we have to explore the whole tree for that. We can't really stop early. Unless we know that we've explored all of the leaves. So you can use either one of those searches to figure out how deep that is. That is also something that you could store. And that way, as you make changes, as you insert or remove from the tree, you could try to figure out, did I just change the height of the tree? But that gets a little bit complicated. You have to store a couple things, the number of nodes at the deepest depth as well as the deepest depth. And that way, if you insert a new node at that depth, then you have to change the associated fields for that. How about deep copying a tree structure? We want to get back another tree, a separate tree with new nodes, not the original nodes, that have duplicates of the value of the data in all of those nodes, or the keys in all of those nodes.
Sorry.
Yeah, basically you can do either one of the searches, but whenever you do the search, you know where you are and you know where you came from. You have to store where you came from so you can make that connection. And then you just on a node by node basis do that copy. So if we had a tree structure. And we wanted to copy this, and let's say it actually had the numbers 1, 2, 3, 4, 5, 6, and 7 in it, in the same way that we might expect from an actual binary search tree. We could do this either way, but let's say we start with the root. We're going to deep copy the root, which gives us a new node with 4 in it. How do we want to proceed? Do we want to do it in the recursive fashion or the queue fashion? Queue. All right, so we're going to add to a list of things to do. We want to have 4's left child, so whatever this node pointer is, that's what's going to be here. So the node that points it to, this isn't the value to, this is the address of that node. We want to deep copy this node. And then we want 6 to be next. So we're going to say, all right, now we're going to dequeue this, and we know that we just came from 4. So we're going to make 4's left child this value. So we're going to make a new node, assign this value to that new node, and say that 4's left child is that value. Then this has been dequeued, which means that everything moves up. We're gonna add, as we do this, 2's children to the to-do list. So we have 6 and now 1 and 3 on the to-do list. So now the 6 is going to become 4's right child, because that's the next thing to do. We have to find some way of keeping track of. The next 2 things are gonna be this particular node, so we're still storing off the 4. Make its left child, make its right child, grab its left child. So we would make this the 6, DQ that, move that down, add the 5 and the 7, etc. So it's a bit more of an involved process, but it works. So that's how you can still use a search to deep copy something. So all of these methods are actually searches, which is kind of an interesting thing to think about. So determining a tree node's depth in a particular tree is a search if we don't store the parent. A tree's height is a search if we don't store it. Deep copying a tree is actually a search. All right, so I've talked about binary trees, and a lot of the interesting trees in computer science are binary trees. So we have at most 2 children. In a binary tree, it is possible to have 0 children if it's a leaf, or 1 child as well. So all internal nodes have either 1 or 2 children. And leaves have no children. This will allow us to store data efficiently. Why do we think that is? If we looked at the guessing game that we played in last class, why is it really efficient to store things in a binary tree? Quiet class is quiet.
I wasn't here yesterday, but would it be, is it easier to like search for the stuff you're looking for?
When you make 1 step down the tree, what happens? Yeah, cuts it in half. We're throwing away half of the remaining tree every time we take a single step. So storing things efficiently is great for searching purposes because we can do a binary search on this tree. Because it is also the same of, it gives us less than, equal to, or greater than. So let's say we have some subtree, and I'm gonna draw the same tree a bunch of times today. Probably just leave it up. But this doesn't even necessarily have to be the truth. Let's just say this is the current node we are looking at. If the value that we're looking for is less than this value, we'll call this Q for the query. If it's less than, it's going to be in this half of the tree. If it's greater than, it's going to be in this half of the tree. And if it's equal to, then it's directly equal to the node that we're currently at.
Is that always?
That will always be the case as long as we do an insertion and deletion correctly. So that is the next thing we're going to talk about, is how do we insert into a binary search tree? How do we remove from a binary search tree such that this stays the same? We want this guaranteed. If the query is less than the current node, then we go down the left subtree. If the query is greater than the current node, then we go down the right subtree. If it's equal to, then we've located it and we can return that node. Here's where it is in the tree. Questions on binary search trees and how this just maps to binary logic? As we move down this, we have a new subproblem where we have equal, less than, and greater than. And you can see that it just continues that process as you move down the tree. So you can define this also recursively. So this says exactly that. Data less than the current node's data is found in the left subtree. Data greater than the current node's data is found in the right subtree. And then all binary trees that adhere to these rules, we're gonna call binary search trees. So we can have a binary tree that does not adhere to that rule and is not a binary search tree. But it still adheres to the internal nodes have one or two children and these have none. So that's a binary tree. If we get this guarantee for less than, greater than, equal to, then it is a binary search tree. Because it can implement binary search. The algorithm. So let's actually start talking about insertion. Because being able to insert into a binary search tree is a very important thing if we want to guarantee that this stays the same. We can't assume that this tree was generated by magic. We may see that we have a bunch of nodes and need to be able to insert them into a binary search tree. So let's think about that process. Assuming we have an existing binary search tree, or maybe not, let's start with the first time. If we have an empty binary search tree and we want to insert something into it, what should we do?
Assign it to the root.
Assign it to the root. Exactly. In general, if we have an existing binary search tree that is of size at least 1, how do we insert into it?
Whatever the root points to.
Kind of afterwards, we need to do this search through the binary search tree to figure out where it should be inserted. Is the thing we want to insert greater than or less than or equal to the root? So let's start shouting out some numbers, and we're going to insert into and starting out as empty binary search tree. Numbers.
17.
Well,
Negative. All right, probably good enough. So we have 8, 17, 3, 25, 112, -1, 1,007, and 2. I like this. It's a reasonable variation in the numbers. So the first thing we're going to do is take this first value and we're going to make a new node, and we're going to assign that new node to the root of the binary search tree. So here is the node that is 8, and this is our root. Next, we want to insert 17. How are we going to do that?
check if it's greater than, less than, equal to the root.
Yeah, check it. Is it less than 8?
No.
Is it equal to 8? Is it greater than 8? Yes. So since it is greater than, we should go down the right subtree. So we need to check, is the right child of the current node null? If it is, we need to make that node and insert it there. If it is not null, then we're just going to go to that point and continue this question recursively. So since 8's right child is null, we're going to make the new node 17 and store it there. 17 has been inserted. Now 3, is 3 less than or greater than 8? Less than. Is 8's left child null? Yes. So we're going to make a new node, give it the key 3, and insert that as the left child of 8. 3 has been done. Question?
How did you refer to, did you say, did you go back that last step?
Yeah,
And you said you checked if, H what?
8's left child
Oh, it's no.
is null. Yeah, each node, remember, if this is the case, then each node, this would be a binary search tree node. And this would be of type integer because we're inserting integers. So there's going to be an integer key or data, it doesn't really matter what you call it. There's going to be a BST node left child. It's going to be a BST node. Right child. It doesn't actually matter whether there's a parent here or not, we're never gonna need to refer to it for the insertions process. But maybe there is also a BST node. Parent. So here's everything that is in the BST node integer. These are all the fields for the nodes. So when I ask about, we start at the root. So we're gonna ask the root's left child or right child, and we're querying whether these fields have a node value or whether they are. Yeah,
For insertion, so like say you had another 8 in that list, how would you add that?
we would either have to break ties by saying this isn't strictly less than, it's less than or equal to go left. Or this isn't strictly greater than, it's greater than or equal to when you go right. And that way, if you have if you're looking for a copy of something, then it's either going to be left all the way down the right subtree, you would find it if you did that search, or right down the entire left subtree. It's a great question, but there is a searching mechanism to find duplicates. We're not going to worry about duplicates for now, but there is certainly a way. How do we insert 25? Look at the root. Is it greater than or less than 8? Greater than, we're going to look at 8's right child. Since it's not null and it exists, we're just going to recursively visit this node and ask, is 25 less than or greater than 17? Greater than. Looking at its right child, it is null. So we're going to make the new node with key 25 and insert it as 17's right child. So this has been inserted. 112, how do we do it?
Is it greater than 17?
So now we finally have a null right child, so we're gonna make a new node with key 112, and that's going to go here. We've inserted 112. How do we do -1? How do we do 1000? We just decided to get bigger and bigger and bigger, didn't we, as we went? We were just trying to outdo the last person who gave a big number. How about 7? Where does 7 go?
Child, 3.
Yeah, we're gonna go, it's less than 8, but greater than 3. So we're gonna put this as a right child of 3. How about 2? Yeah, less than, greater than. So down here somewhere, we're going to have a 2. Just from this, does it look like an efficient structure? Kind of. It's a little bit better than a linked list, but not really. So this is why it's important to keep these balanced, because there are places where we could have nodes that are empty, like right here. There's nothing, and it's only 2 away from the root, but we have something that is 1, 2, 3, 4 away from the root. That seems suboptimal. We can also store something here, or here, or here, or here, and all of those are 3 away from the root. So the fact that there's something that's 4 away from the root, and there are places for things that we could store something, could we come up with an equivalent tree that stores all of this data that is not this deep? We could. In fact, it's really easy to do. All we have to do is kind of shift this right here, where this becomes 17. This becomes 25. This becomes 112. This becomes 1000. You don't need this node anymore. We took out one depth from this, and now regardless of what your query is, the worst case performance of this tree is now better. So I'm not gonna introduce the couple of ways that we can balance a tree as we insert and delete. I will leave that to algorithms. But just know that this structure is not efficient without handling that. We don't get much of a guaranteed boost from using a tree unless we balance it as we insert and delete from it. All right, I'm gonna leave this tree up here. Because now we need to figure out how we're going to delete from this tree. So how do we delete? Let's start with the easiest case. Let's say I want to delete 2. What do I need to do to delete 2?
Or 2 to 8.
Yeah, we need to start at the root because we don't know where 2 is in the structure. But we can find it with exactly this same logic. So 2 is less than 8, so it's gonna be down the left subtree. Now all of this gone. Is 2 less than or greater than 3? Less than, we're gonna go down the left child. Less than or greater than -1? Greater than, hey, look, we found it. So you're gonna be comparing the query to the data of the node. If it's less than, you're gonna visit the left child. If it's greater than, you're gonna visit the right child. And if it's equal to, that means you found it and you can apply the delete algorithm to it. So we just need some kind of if statement that now says, is it a leaf? What would that if statement look like? Yeah, if the left child is null and the right child is null, then it's a leaf. How do we delete 2 once we have found it? Is there anything that we need to consider?
No, you can just go back to the 1 and just eliminate the stretch out, right?
Yeah, so if we have a parent, we can just go right back up to the parent. But we don't necessarily need the parent if we store kind of the very first thing you do, you create a parent, and when you visit, the parent doesn't move. And then as you move, you just keep track of the last node that you were at. And then you can query that parent's child for the direction that you went last time. And then you can modify its connection to remove it.
Is that kind of how, what you just said? -1's right child and null.
Yeah, -1's right child is null. That means there's no way to access the node that is 2, and since we're in Java, there's a nice garbage collector that's gonna go remove that for us without our having to think about it. So 2 is gone from the tree. Great. So in general, that is how you delete a leaf. You do a find on that. That gives you the node, and you need to change the parent's associated child, depending on how you went from the parent to that node, change that associated reference to null. How about a one child delete? So let's say we want to delete 112. 112 has a single child, it has a right child without having a left child.
Similar to linked list where you have 1.5 and the 1,000.
Yeah, so if we store the parent and child, so we would compare, we would still do that find process. We would say 112 is greater than 8, it's greater than 20, oh look, we found it. If during that process, we stored a parent and a child as we went, we want to query if the child has a left child but not a right child. Or if the child has a right child but not a left child, then we're in the one child delete. So we need to do something like change this reference to instead of pointing at 112, to instead jump over it and point to the child's child. Is that the same thing if this were to be something like 70? Let's say this node 1000 didn't exist, and now 112 has a left child but not a right child. What logic should we have there?
Child to the parents.
We actually don't, because we know it's also greater than. This is always going to be greater than that, regardless of whether it's a left child or a right child. So there's actually no new consideration, depending on which child it is. So regardless of which child exists, you just change this parent's right child to be this or that, depending on which one it has. The difficulty is the two-child delete. So one child is also not that bad. So this just removes that node from the tree. And now we have, I'll just draw this again as a single node, but we didn't actually change anything. Great. So deleting with one child, not too bad. But again, we want to store that parent and child as we go. Let's talk about the hard one, the two-child delete. Any questions on the one-child delete before we move on? Yeah,
I'm still kind of confused on how you get to that. Child, you just call the child up next, I guess.
child, yeah, right child or left child, you need an if statement that says. Let's say this node is called C. C dot left child is null. And C dot right child is not null. That's one of the cases of the one child delete. The other one is if C dot left child is not null. And C dot right child is null. So if you're in either one of these cases, then it's a one child delete. And then if you correctly, as you've done your find, done the parent and child, you have access to the node that is P and the node that is C. Then you could modify P's associated. We have to store where did we come from? Did we come from P's right child or left child to get to C? Other questions? Does that make sense? All right, the two-child case is easier than this to identify. If C dot LC is not null and C dot RC is not null, then we have a two-child delete. That is harder. We can't just make a single connection and make this work. So let's say you wanted to delete 25 now. What options do we have?
Could you compare the two child nodes, and that could be how you structure them here?
Yeah, so we either need to bring the 17 up or we need to bring the 1000 up. And that is complicated if there are left and right subtrees to that. So let's say we want to delete this, so here we have the parent, here we have the child, but now imagine that there is a 10 and a 20 down here. And we want to bring the 17 up. I'm also going to insert things here, just so that we see the full scope of, we have 800 here and 1200 here. So now we can't just easily determine, we should bring the 1000 up and not worry about it. Somehow we need to delete 25 from this tree. Think about it and talk it over with your neighbors, see if you can figure out a method to get rid of this 25 and maintain a complete binary search tree. This should be a constant time procedure regardless of the depth of the tree. It's not a constant procedure, but it is a logarithmic procedure. Yeah.
Could you make the two child, into one child and then have it? Go back and have that later?
So what needs to change if we were to bring the 17 up? What is still legal and what is not?
Could you bring the 17 up and make 1,000 the parent, the right child and 20? That's the ones.
Okay, I like that. That's a start. So we're gonna bring the 17 up to the 25. We're gonna change this data to be that data.
If it's not efficient, at least maintains structural integrity.
What of the existing substructure here is still valid? Yeah,
Can you just move 1,000 over and then move the children of 1,000 to be the child of, the node we just changed?
we still need to deal with the 10 and 20. Those still need to, I mean, the 1,000 over here.
Yeah, we moved the 1,000 to that node and then we make its children.
The
child.
issue is that now 1,000 is not less than 17.
Oh, yeah, shoot.
Before you like move the 17, you know, compare the 17 and the 1,000, which one is bigger, like to move it to that.
We already know this has to be bigger because this by definition was less than what was here, and this is greater than what was here. Because they are associated left and right children.
Is doing that right there, isn't it making the 20, I guess, making
Yeah, we made a
25?
problem.
Yeah, isn't that gonna be null now, so you can't get it? to 10?
Correct. So we're going to delete this node and attach here. And what we have is this dangling node here. What do we know about this and anything about its associated subtrees?
So
It doesn't have to be.
It's very low.
So everything that is down 20's left child has to be between this node's value and 20. So the range of what's valid here is something between 10 and 20. This is gonna be between 20 and this value right here, 1,000. Yeah,
Insert it between 17 and 1,000.
we're gonna, yeah, that's exactly right. If we go from this point and go to its right child and then all the way down left, 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 left. Until we hit a leaf. That is where we insert this node. And its entire subtree. Whatever this happens to be, it actually wants to go right there. So this gives us two cases that we need to consider. If we're moving up and attaching a left, then the right subchild of that has to be inserted as this node's left, 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 left. As soon as that left is null, that left child, that's where that subtree goes. And it's the exact opposite if we attach the right, and we call this orphaned, we orphan the 20. It's a terrible name. We orphan the 20, and then we have to reassign it to a foster parent. And in this case, the foster parent is going to be the 800. We took to find the next largest node in the tree. That's after the 20. The next largest node is going to be this 800.
That was a garbage collector, no, not to pick it up, because now it's not connected.
Luckily, we're going to have some reference to this in the scope of the delete method. So we're going to have something that's like grandchild GC equals this node. So that's the reference to that node. If we were to end or remove, then GC would go away and the garbage collector would eat this. But if we attach it to something like the left child of 800, then that, I should say this is not between 20 and 1,000, this is between 20 and 800. Not 1,000. Because if anything, if here had been less than 800, it would have been inserted down here. And not as the left child of 20. In order for this binary tree to be valid.
And this doesn't change the balance of our tree at all.
It definitely does. So after every single insertion and deletion, you have to go through a balancing procedure. But all of the balancing procedures that we have are logarithmic in nature. So it allows us to, with a logarithmic time procedure, ensure logarithmic time insertions, deletions, and finds.
Why can't you just assign 20 to make 10's parent?
To 10's parent,
Why couldn't you make 10 or how, like, make 20 10's child? Did you not do that?
because now if we did that, then 20 is greater than 17. So it breaks the binary search tree rule. We know that in order to go left here, we have to be less than 17. So we need to insert this 20 somewhere in 17's right child, right subtree. It's a great question. So we start getting very algorithmic as we start diving into the why behind how tree-related algorithms are done. But I think the important things to take away from today is find, which is the process of starting at the root and asking, are you less than or greater than or equal to, and continuing that process until you locate the node. Then the process of insertion. That is a find followed by changing some node reference to be a new node with the associated key of the insertion. And the fact that deletion is 3 cases. There's an easy delete a leaf case. There's an easy delete a 1-child case. And there is a much more difficult delete a 2-child case. Where we have to now break this down into some additional cases of what are we moving up? There's a correct answer here of what we do. We can either move this up or this up. But if we move this up, we're gonna orphan this node's right child. And if we move this up, we're gonna orphan this node's left child. And so the insertion for that is either all the way down right left subtree or down left right subtree for where we make that connection. Because that's where the next smallest or next largest elements of the tree are going to be. Like for instance, if we completely got rid of this for the moment, where is the next largest element in this tree larger than 17? It's down 17's right, left, 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 left. You just continue to follow that process until you hit a node left child. And that is the node that is the next largest node in the tree. What about the next smallest? You go down the left, right, 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 right. It's smaller than this, but it's the largest thing that is smaller than this. It is larger than this, but it is the smallest thing that is larger than this. And that's another way to kind of define the next largest or next smallest node in the tree. All right, we're out of time. We're gonna come back and talk about tree traversals next time. And the different ways that we can actually traverse a tree. I apologize for those remote and how difficult it was to understand what was going on. I'd be happy to meet individually with any of you and try to word this differently or give you some of these visuals that are obviously really difficult to get remotely.